quite a bit of an interaction with my very first year here at Lawrence. He was my summer student my very first year. I started as a tenure line faculty, and we had a grand adventure. And I took him out to North Dakota, South Dakota, and Montana, and we drove around. And if you really want a story, ask about the night that I came out and David said, "Dr. Donahue, have you seen my tent?" His tent had disappeared. It's a lovely little story. We found the tent. I did bring him home safely, and we got wonderful data from that adventure. We did have to give it some surgery and stitch it up, but we did find it. Since that time, David has had lovely adventures out at Moat Marine Lab and has decided to kind of work on a topic that's a little closer to his heart because of his presence here in Appleton, and he'll tell you more about this. He grew up in Appleton. He's a hometown boy. And so he's going to talk about PCBs today. And after this, he actually is going on to MBARI, Monterey Bay Aquarium Research Institute, to work with people who were the advisors of my RU from when I was an undergrad. So a lot of following, well, me pushing him in my footsteps.
I'll take it.
Just David has been a joy to work with. This project is totally of his own devices, and everything that you see here is of him. And I just kind of said, yeah, go ahead and do that. Yeah, keep going. And I couldn't be prouder of how far he's come and what he has done. And with that, I will pass it off to you.
Okay. Well, first off, hi everyone. If you don't know who I am, David was just introduced. And I was actually born and raised in Appleton, Wisconsin, so this project really does hit close to home, looking at the toxins in our backyard, specifically the Fox River to your left. And we're going to be looking at PCBs, which are used in the paper industry, which is what, like Appleton and Neenah was really well known for through its development. So I'm going to walk you through that process and kind of look at my interest in environmental chemistry and see how that ties in. So first off, PCBs were first introduced into the US in 1929, quite a while ago. They're a really great addition. At first, we see a bunch of different products that they're used in, such as lubricants, transformers in a lot of your electronics, heat transfer fluid found in your automobiles and different types of engines, and lastly, paint, specifically the plasticizers inside of that. So there are a lot of different applications. Once again, I want to emphasize that in the 1930s or so, this was a really great invention. And why PCBs were so special is because it stands for polychlorinated biphenyls, which is the PCB itself. And you're going to take 2 benzene rings, and you're just going to attach, in this case I just chose 5 chlorines, and you're going to fill in the remaining spots open with hydrogens. And you can have up to 207 different types of PCBs, whether you have 1 chlorine and it can bond to different spots on it, or you can have up to 10. Really depends on the chemistry that I'm interested in. So what are some of the aspects of this? It's insoluble in water. It's going to be a very combustible liquid. It's going to be inert with all these chlorines. So the more chlorines you actually have on it, the less the more inert it's actually going to be. And where the chlorines are added does come into effect. I'll talk about that a lot later. But for example, if you have chlorines in the planar position, that's going to be very inert. And since it's inert, it's going to be really stable and have low biodegradation, which means that these things are going to last for a really, really long time in our environments. So after they started being produced, actually pretty short after, we start to see some human health effects. They're not too big of a concern, but in a factory where PCBs were first being introduced, we see 23 out of 24 people start to experience small things such as this, and also loss of energy, appetite, and sex drive. So this wasn't really seen as too big of a concern yet. There weren't a bunch of case studies on this. So we're going to start producing these in the Fox Valley. Specifically, we're going to be using them as transfer agents in your carbon copy paper. So whether you're taking a Gen Chem class and you're using the extra duplicate side, or you're writing checks, we use a lot of carbon copy papers in most of our everyday lives. And during this time, we're also going to see a lot of environmental concerns from PCBs. And these environmental concerns come from it having a really long half-life. So as I said before, it's not going to react very well. It's going to be pretty inert. And a half-life is just looking at how long it takes for its initial concentration to go to half of what that is. So in the atmosphere, it takes about 3.5 to 83 days. This is a pretty big range, as you can tell. And this is just because there are different layers in the atmosphere, there are different components in there. It's really going to depend on what your environment actually is. Moving along, we have water, which is going to last even a little bit longer than that, ranging from 17 to 210 days. And ultimately, soil, we don't really know. So PCBs, once again, since they're inert, they're usually going to go from, let's say, the air to the water and then eventually into the soil. They're not going to react, and they're going to stay there for a really, really long time. So we don't have a bunch of information about what their half-life is actually at this stage. And as we start to have PCBs in our river systems, in our sediments, we're going to see that these cute little fish over here, in like their baby stage, is going to startly accumulate PCBs over time because they're going to be stored in their fat tissue. They're not water soluble, so they're not going to be excreted like your regular water soluble metabolites. So you get to see the PCBs increase in concentration in the fish over time. And why do we really care? I mean, fish are cool, but are they that cool? Well, it figures we, in this case, we actually eat the fish, or in this case, the seals and the polar bears. So this is actually going to bioaccumulate over time, meaning that whatever's at the top of the food chain is going to have the highest concentration of PCBs. And that's pretty terrifying because we're at the top of, well, pretty much every food chain, so we really don't want these PCBs in us. And so they're going to be produced for a while, and eventually they're actually going to be banned by the EPA as part of a 3-year phase-out period. So during this period, they're going to pretty much tell factories, hey, PCBs aren't really good to use anymore, so we're going to give you 3 years to stop production of them. The problem is they're still going to be present in a lot of the previous components that I talked about, so we're still going to see these in a lot of electronics and lubricants and things that we used back then or that we still use today. And eventually, in 2009, so pretty recently, we started a Fox River cleanup project, which I'll get into in a little bit. But this is pretty much just to get rid of all the PCBs in the Fox River, which is a really big concern. So if none of you know where you are right now, we're in Wisconsin, specifically here, which is Appleton. And we're looking at the Fox River that flows north from Lake Winnebago to Green Bay itself. So if we zoom in on that image, you can see Appleton in the lower left corner, Green Bay all the way up to the top right. And we're going to see De Pere is kind of close to Green Bay. I'll get back to that in a second. But most importantly, you're going to have paper companies all along this Fox River, located at all these different spots. We have 7 really big ones. And eventually, you're going to see that the PCBs, they just dump them into the Fox River themselves. And this cool animation that shows that. And eventually, we're going to see that the highest concentrations are really going to end up in Green Bay and pretty much anything that flows north. Okay, so the Fox River cleanup project itself, the goal of it was really to get rid of all these PCBs in the Fox River that, for the most part, aren't really going anywhere. And it's a Superfund site, which means that the EPA decided to pool a bunch of money in it because it really was a big environmental concern. And it also paired with the Wisconsin DNR department as well, so there's money coming from a couple different resources. And they decided that, once again, because pretty much everything ends up in the sediment, that they're going to try and clean these PCBs out of the soil in the bottom of the river. And when I'm talking about cleaning up, what does that really mean exactly? So the De Pere area that I talked about, that was near Green Bay, their cleanup project was completed in 2012, or 3 years after the whole cleanup project started. And they had PCB concentrations as high as 3,000 parts per million. So for an example, that is 3,000 PCB molecules in a million molecule mixture, in this case most likely just water. And clean is pretty much reducing that 3,000, which is a ton, down to 50, which is a lot more manageable. And I'm just going to get into that in a little bit. And how do we actually do the so for fun facts, they've invested over 2,206,700 hours as of this early May. Since this is a Superfund site, they have a bunch of really accessible information on this. So this stat came from early May of this month. And if you were to work a 40-hour work week for taking only 2 vacation weeks off throughout the whole entire year, you'd be spending 1,106 years to clean this up all by yourself, which sounds pretty bad. And if you were to treat all of the water that they're taking out of the river, which is about 6 billion gallons, if you relate that to something like your average size Olympic swimming pool, you're looking at 9,000 of these pools are actually being cleaned. So just to emphasize, this is a really big project, huge concern right over there that we need to address. So how do we actually do that? The first step of that, I'm just going to show a video that's easy to explain, which is called dredging. So that's going to be your hydraulic dredge, which is going into the water itself. Get these cool anchors that go down. And then you're going to actually be taking the sediment out of the river and then to some type of processing facility down the way. So the goal of this is to remove all contaminated sediment. It's easiest just to get it out there and treat it somewhere else than worrying about it in the water itself. And the dredge size really depends on the thickness of the sediment, the water depth, and really like how easily we can access this. So we have two different sizes of dredges that we can use. We can use a 10-inch hydraulic dredge, which is going to be for really high contaminations. We're trying to get a bunch of the soil out there. Or we can use a slightly smaller, still pretty big hydraulic dredge, which is going to be at lower contaminations, and it's going to be in shallower water where maybe the 10-inch one can't access. And eventually, it's shown just in the video, we're going to transport this somewhere offshore, and we're going to treat it somewhere else. So once we take out the sediment from the bottom of the river, we're going to cap it, which takes place after we dredge it. And this goal is to trap any remaining PCBs that are left over from pretty much being stirred up or whether we just couldn't access it. So we're going to add layers on top of the sediment bed, and it's going to just trap the PCBs, make sure they can't react with anything, make sure no fish can eat them. And the thickness of these layers is going to be dependent on the actual concentration of the PCBs. So for a little bit better visual, we can have three different types of capping present. We can introduce a 33-inch cap, which is going to have really your highest concentrations of PCBs ranging from 50 to 10.5 parts per million. And most of these caps are just going to be made of a little layer of sand, and then in this case a really big layer of rock. And then for a smaller cap, if you don't have that many PCBs present, it's going to be 10.5 to 2 parts per million. This is going to be a 16-inch cap, have the same amount of sand, but less gravel. And then eventually your 6-inch cap, which is going to be pretty much after you get rid of all PCBs, but you want to make sure that there's nothing left over. And if for some odd reason you have a PCB concentration higher than 50, you just got to put the dredge back in there and just get more sediment out. And eventually we're going to take this to the processing facility where we're going to remove the sand, which makes up most of the sediment itself. We're going to filter press it, which is kind of pictured to the right over there, where we're removing the fine grain in the water, and we end up with these massive sheets of PCBs, which are pretty cool. And we're going to treat the water, and we're going to either put it back into the facility to run its processes, or we're going to return it, treat it really well, back into the Fox River itself. And once these giant PCB sheets kind of like fall off onto a conveyor belt and move it to a truck, we're going to take that to the Calumet County landfill, which is going to be specific for treating different type of toxic materials that aren't in your typical, or shouldn't be, in your typical garbage bag. So there are a couple different ways to destroy PCBs once they either get to this plant or natural environment. They can be incinerated at 12,000 degrees Celsius and produce your carbon dioxide, hydrogen chloride, and water. These are good. This is safe. This is going to be a great incineration. Unfortunately, if you do something lower than 1200 degrees Celsius, you can get some really weird looking stuff like this polychlorinated dibenzyl furan. And this occurs by if you incinerate it just a little bit, you can take one of the chlorines off, make it super reactive, and then it can just kind of do some crazy stuff with other molecules that are present there. So I'm not going to get into that too much, but how you actually incinerate it makes a big difference. Another way that you can destroy PCBs is through sodium naphthalide, which is used as a reductant, so that's just going to break up your carbon-chlorine bond, get rid of the chlorines, treat it that way. Or for all you biologists or biochemists out there, you can use a bacteria called Shionella oneadensis, which is it can run in, I think, it can run with either oxygen or without oxygen, and it has an elevated transcription of cytochrome C. This is found in your electron transport chain, which deals with electrons, and this is also going to be able to reduce your carbon-chlorine bond. And that's pictured by those guys over there. So we look at the Fox River cleanup project, what's going on. what the heck am I supposed to do here at Lawrence? So that brings me to my research questions and what I really want to accomplish in this, my time still here left. So I want to look at a way if we can even detect PCBs in a known sample. So if we order something off campus that has PCBs in it, we use something here that can actually tell us for sure that we have them. So we're going to have to find an analytical technique to use this. And in this case, we're going to use a separation technique, which is called gas chromatography, and an identification technique called mass spectrometry. And eventually, what I really wanted to get to is to look at extracting them from soil samples at different points on the Fox River. It would be really, really cool to see if the EPA is actually holding up to their standards of what they consider clean or not. And so that's kind of where I'm geared towards. So if you pair the GC MS together, those two techniques, you get this really cool instrument called gas chromatography, mass spectrometry, which I'm sure most of you used in Orga or inorganic or just for fun if you have. And this method was developed in the 1950s. It's been around for a while. If you put a sample in back in the 1950s, it could take about 20 minutes or so is the fastest you could do. If you run the same sample with similar methods now, it can take about 90 seconds. So this instrument has come a really long way, and it's a great way to analyze things quickly without having to wait around for a really long time. And it can detect trace amounts of chemicals, whether it identifies what you have in there or how much in there. This is a great technique for both of those things. And we're going to find that it could be used in a lot of different things other than really small scale chemistry ideas. So in this case, this GC over here is actually used on the Viking mission, where they looked at the different gases present in Venus as well as the soil concentrations on Mars. It can be used in your food and beverage industry, whether you're looking at what makes up the flavor of your food or beer, so terpenes and other ethers or organic compounds. And you can also look at contaminants in food, so what made it go bad. It can also be used for forensic science, so whether you're looking at anabolic steroid usage and other performance-enhancing drugs, you can look at that. But for the sake of my talk and what I'm really interested in, although all those sound cool, is the environmental chemistry side of it. So we're going to see, it's been also used for insecticides and herbicides, but I'm going to see if I can find out if this stuff is present in soil samples. So, first part, we're going to separate it using gas chromatography. For all of you that don't know what it is, here's a quick crash course on that. So we're going to separate the components based on chemical properties, typically polarity, and how well it's going to stick to a column. We're going to have two phases of that. The first phase is going to be a stationary phase, which is the coating of the column itself. And then the mobile phase is going to be the inert carrier gas. We want the gas to be inert so it doesn't react with anything, give some wacky products that we have to look into more. So let's just make it inert, make sure it doesn't react, and we'll go from there. And we're going to have three different separations that can happen. We can have it condense in the stationary phase, we can have it dissolve in the liquid on the surface of the stationary phase, or we can have it remain in the gas phase itself. So this is the column, the black part coated with the green. We're using a coated column because this thing is super, super thin. So if you imagine like a circle, it's literally coated on the outside, opposed to most of you have probably used stacked columns before. So just a FYI. So we're going to add our PCBs, which is this purple line. It's going to have a mixture of, I said, up to 207 different types. We're going to use our mobile phase, pictured here, the helium gas, so that's like the center of the column. And then our stationary phase, which is a phenyl methyl polysiloxane column. It's pretty standard. You don't have to worry really too much about it. And eventually, after we add the PCBs, we're going to see that they're starting to separate based on how big they are, how many chlorines there are, where the chlorines are actually present on the PCB. And we're going to see that change over time. So just for the simplicity, let's label this one PCB 10 and this one PCB 100. So eventually, they're going to come out of the column at different times. Notice that PCB 10 comes out before PCB 100 is even out of the column. And this is going to be the best way to separate these components. So we're, once again, taking our carrier gas. We have flow controller, which just tells us how much gas is going into our system. We've got our sample injector, where you just put the sample, self-explanatory. And we're going to run it through the column, which is located in an oven. We want to make sure that the sample is really, really hot so it stays in the gaseous phase and it can move through this column. And eventually we're going to run into a detector, which gives us this kind of okay looking chromatogram. And the detector itself is going to be our mass spectrometer. mass spectrometer. So that's the second part. We're going to run our source. We're going to have our source, shoot it with an ion beam, which is just some type of filament, induce it with a magnet or magnetic field, and we're going to see separations of our lighter or heavier atoms based on their atomic weights. So if you see CO2 based on its isotopes of carbon-12, carbon-13, carbon-14 are going to come out of the mass spectrometer at different times, and we can detect the fragments of these molecules. Pretty sweet. So I'll get into how you actually read the graph in a second, but this is what a typical mass spec graph would look like for carbon dioxide. The x-axis here is going to be your MZ, which is called your mass to charge ratio, and then your abundance is going to be your y-axis, which is pretty much relative in this case. We're just looking at how it stacks up compared to other molecules. So if it's like 20 or 30, it doesn't really matter too much. But we're going to see that carbon dioxide usually breaks off in one fragment with a mass to charge ratio of 44. Let's compare it to something else just for kicks. So let's try propane. We're going to see that there's a ton more different fragments that we can have, mostly because, well, there are more elements present in propane itself. And then where actually these atoms are bonding really does matter a lot, because you can tell cycle of propane changes the abundances around this 40 compared to your propane. So how the isomer of whatever molecule you're looking at really does matter when you're looking at mass spec abundances. So let's go back to propane and kind of analyze what we're supposed to look at with one of these kind of strange looking graphs. So we have a regular molecular ion, propane, with an atomic weight of 44. So this is anything to your farthest right is going to be the largest fragment, or your regular parent molecule that's just ionized. It's not going to be broken into anything yet, because that's as big as it can be. Moving left, we're going to take just one hydrogen off there, and we're going to produce a mass ratio of 43. Eventually, we're going to see the highest abundance is going to have a mass ratio of 29, where we're just going to lose a methyl group. Eventually, we're going to take one more hydrogen off that, and we're going to detect that methyl group that came up over there. So now we finally understand kind of what GCMS is. So let's compare it to a previous study. And in this case, it was done by Cirrus, and this title looks a little intimidating, but we know what PCBs are. We know what GCMS is. So now we really just have to look at this standard chlorine metachem site. And I always thought this would be kind of like a cool 60 minutes or something. It's kind of shady with the EPA, but it's a super fun site. And this company that was producing PCBs in the 1960s they started producing them. They didn't really abide to a lot of EPA regulations, especially in the 1990s. They mysteriously went bankrupt in the 2000s when the EPA started really contacting them, getting on them for not abiding to anything. So then they shut down and didn't clean anything up. So then this method is just looking at a way to detect what PCBs and how much crap they pretty much left behind. So this cool looking extension arm on this just type of machinery goes like 90 feet into the ground and is trying to get all these PCBs that eventually leach into the groundwater. So this is a pretty big concern as well in other places other than just the Fox Valley. So let's take their study and see if we can apply it to what we have here. So we have this GCMS parameters. You don't have to worry about it too much, but that's your GC over here. We're going to have the column and the column oven. Once again, I just said this is a standard column. You don't really have to remember it or anything. But it is interesting to note that it's really, really long. It's 30 meters. And this is just to make sure that you have really good separation between all your different PCB congeners. It's going to have a diameter of 0.25 millimeters and a filament size of 0.25 micrometers. So super small, really long. And lastly, we're going to inject with our syringe. It's going to be about a couple microliters or so, at an injection temperature of 280 to make sure, once again, that all these are in the gaseous phase when they run through. And so what are we actually injecting? We're going to use a standard, once again, to make sure we know what's in our sample to see if we can detect these PCBs. So we're just going to use this mix that we found at Sigma Aldrich that contains 10 micrograms per milliliter of each congener and heptane. There it is right there. It only came in a milliliter size, so it only comes up to about this line or so. But that's totally fine. We're working with really small, once again, I said microliter amounts, so this will last us for still years to come. And this is actually all the different PCBs that are in our standard. I wouldn't even worry about all this stuff, but I would just look at for right now the number of PCBs. So we have a pretty good range between 3 and 8 to see if our detection can actually work. And then our congruent number, which is between 0 to 207, increases as the number of PCBs increase. So if you see a PCB of 18 later in the talk, just think that's pretty small, not too bad. PCB of 194, that's really big. So we're going to inject our sample into the GC MS using the following RAM cycle. We're going to hold it for a little bit, make sure that our sample gets nice and cozy inside the column. We're going to ramp it up, which starts our separation technique for about 5 minutes or so. We're going to hold it really briefly again to make sure that everything is equilibrated, and we're going to ramp it up even more. So in this case, we're hoping to see the most separation in this part because the PCBs have already been in the column. We're increasing the temperature a ton, and hopefully in our chromatogram we'll see something in this area. And then lastly, we're just going to hold it for a little bit longer to make sure that everything that we put in the column is going to come out of the column, and that's going to be at a really high temperature, just to double check. And this only takes 22 minutes. This is, in the chemistry world, actually pretty incredible how fast this takes. So if you're an organic chemist and you're trying to synthesize things, that's going to take a really long time. This is 22 minutes. You do like 3 of these or so in an hour. This is a really great technique to look at different molecules. So what does our standard actually look like when we run it through the GC MS? It looks like this. So this is really great. This took a lot longer than I was hoping to get, but alas, we have 10 different peaks with really good separations. And as I mentioned previously, we're starting at about 9 minutes and ending at about 15, which is where we thought our separation would occur the most often. So our separation technique worked great, but we need to figure out if our identification is spot on as well. So let's just go left to right. We'll start with this smallest peak, zoom in. I know it's not the best looking since it's not perfectly peaked, but it goes up a little farther in the front, like goes down. It just means it's a little bit oversaturated, nothing to be concerned of. And we're going to run it through the GC MS. So this graph still looks a little bit intimidating, so let's break it down a little bit. Our farthest peak to the right is once again going to be our atomic mass, which is going to tell us the bulk of our parent molecule that's just ionized but doesn't actually lose anything. So we can determine for sure that this has 3 chlorines on it, which we'll just throw the chlorines in this position for now. Eventually, we're going to have a fragment where only 2 chlorines are left, denoted by this 2:1 mass to charge ratio peak. We're going to do that one more time to have 1 chlorine left, and even one more time at your 150. So we can say with confidence that this peak for sure, or this graph for sure, is telling us that it's a 3-chlorinated biphenyl. Unfortunately, in our sample itself, we have 3 different PCBs that have 3 chlorines on them. We have PCB 18, we have PCB 28, we have PCB 31. So we have to go a little bit more in depth than that. So is it PCB 18? We're going to stack what we know, which is in the red, or what our mass spec told us, to what a regular PCB 18 would look like in the mass spec library. So what we actually got is in red, and what the computer thinks would be a PCB 18 is in blue. So it's actually really, really hard to see, which is a really good sign, because that means that this is probably going to be PCB 18. If we just look at this and we're looking at these 4 peaks. And if we look at this a different way, in a difference graph, we're going to see that this matches up pretty well as well. And so anything that we ran in our standard is going to show up in red on the top, and then anything that didn't show up is going to be in blue. And then the difference between those, so if there's anything that is really present in one but not in the other, we're going to see that in green. So in this case, we see that all of the peaks where our chlorines are going to be really close to 0, telling us that this is actually a really good indicator that this might actually be PCB 18. But let's check out PCB 28 just for fun. So we can tell that the peaks are still there. There's a little bit of a difference in abundance between red and green. I know it's tough to see. This is the best picture I can get, but the red's up here, blue's down there. I think red is there and blue is there. So the abundance isn't matching perfectly, but we still see all of these 4 peaks, which means that it has 3 chlorines on it somewhere. So we go to our difference graph, and we see some pretty big differences here in both of these chlorine peaks. So we're not super confident on PCB 28. Let's still stick with PCB 18, but we still have to check our last one. So for PCB 31, we can tell that we have all these 4 peaks. It's going to match a 3 chlorinated biphenyl, but once again, our abundances are going to be pretty different for at least one of the peaks. So we're going to run it against the difference graph once again, and we're going to see that there's a pretty big difference between the 3 chlorinated and the 2 chlorinated fragment abundances. So being the wonderful chemists that we are, we're not going to jump to any conclusions right away and say that this is PCB 18, but we're simply just going to group based on our mass specs that the following are just 3 chlorinated peaks. These ones are 4, 5, 6, 7, and then 8. So this we are absolutely certain in. We can tell which peak has how many chlorines, but the abundances aren't really matching up perfectly, and we could stop here, but I kind of want to go a little bit farther and assign a PCB for each of the following peaks. So how do we do that? We will go to another source, which in this case they're just looking at PCBs in transformer oil using the same method, GC MS. And they found the different retention times of a bunch of different PCB congeners, in this case 82, and they range from 0 to 207. So this is a really great range, once again, to look at what's in our standard because it covers a bunch of different congener sizes. So for just an example, PCB1 versus PCB118, which both have 5 chlorines on them, are going to have really, really different retention times. So this one's only 21 minutes, this one's 24. And even though these retention times don't match what we have, that is totally okay. We used different parameters. Even though we had the same column, they just ran the experiment different than us. So we're just going to say that PCB 118 should come off after the column before PCB 101. So we go back to this graph, and after pulling the retention times from the following source, we're going to replace all those with the following PCB peaks where we expect to find them. And this is really great. It took a while. Got this spring term like a couple weeks ago. So this is a really, really good sign. So we can finally say that our GCMS has a method that can detect PCBs in a known sample. So that's super cool. So our method works, but I still want to kind of do this with something else. So I found this river sediment A that literally Dr. Deanna Donahue and Daniel just handed to me one day. And that's a picture over here. It looks pretty old. There's a weird stain over there. We don't really know a lot about this. And it's going to be an air-dried river sediment from the Hudson River. And it's going to be taken out of there and radiation sterilized with C60 or your Buckminster fullerenes, big nanocarbons. Chris is nodding his head over there. He knows what's up. And eventually, we're going to get a certificate of analysis where they're going to run these tests based on what they put in that little bottle. And they're going to tell us what we're supposed to detect and how much of it. And they're going to say that in the example of this certificate I found, there are 64 congeners present, and it tells you how much is found. I didn't want to get into that too much. And this is really cool, so now we can try what we learned in our standard with a soil sample, and we can look at like how to extract it from that. The only problem is we don't have our certificate. Daniel really just handed this to me one day, and we have no idea what's in here. It could be dumped out and replaced with something else. For all I know, we really don't know. So how do we actually isolate this? We take our PCBs in that bottle. We've got Daniel holding some hexane here. Mix it together. And then you're going to isolate your PCBs in the hexane. They're going to be soluble in an organic solvent. You're going to have kind of all your river sediment crap on the bottom there. And unfortunately, since our syringe is in terms of microliters, we're going to, I got it stuck a couple times and broke a syringe or two. So we're going to have to we're going to have to isolate the PCBs one more time using just a regular organic filter and a plastic syringe. and eventually we're going to come up with this beautiful, pure-looking PCBs dissolved in hexane solution. So let's run that through the GCMS and see what we see. So now we have these really good peaks, once again, between 9 and 15 minutes. So it honestly looks like there could be PCBs in here, which is pretty cool considering we don't know what's supposed to be in there. So let's use our same technique. Let's just zoom in on any of these peaks. In this case, it's at 12.46 minutes. We'll run an MS on it, and we don't really see any chlorine peaks, which is a little bit concerning. The best our MS library can give us is this weird looking 9N hexylheptadecane, which doesn't have any carbon rings, doesn't have any chlorines on it. It has a pretty big difference based on the graph I didn't include, but that's pretty strange. So no worries, okay, it's fine. We'll pick a different peak. This one's at 13.01 minutes. We'll see what let's see what the MS says on this one. And we see the same thing. So there's no chlorine activity over here. There's some kind of crazier stuff over to the left here on smaller fragments. And we're going to see it gives an N-tetracantane, which I'm not looking a bunch at what these really are or how the PCBs would produce this. We're not even totally sure that this is what our mass spec is telling us, but this is the closest product that we can see. Alright, so we're a little disheartened at this point. Let's pick one peak just for a saving grace, hopefully. This one's at 13.39 minutes, and we see that, and we match it with a 3-benzyl-2-phenyl-2,3,4,5 tetrahydro-1H3-benzophenine. It's not a PCB. It's getting a little closer. We see some carbon rings. We see no chlorines. So this is a little bit of concern. We didn't see what we were expecting to see, but at the same time, that's really okay. We had no idea what was actually in this river sediment since we didn't have our little NIST certificate. So that's all right. And now, looking forward for future work, we can at least say during the scope of my year working on this that we can identify PCB congeners using GCMS. I really want to emphasize that this is really cool. I hope that someone else in this crowd maybe pulls this for a future research experience topic. And we saw some weird stuff going on with river sediment A. At the same time, that's okay, because on the NIST certificate, it said that it was supposed to be stored in accordance with the instructions given in the certificate, which was it was supposed to be closed to make sure you couldn't get any water to react with it. It was supposed to be stored at 25 degrees Celsius or cooler, and it was supposed to be stored in a dark place to make sure that light wouldn't break up your PCBs. And we have no idea if any of that was true. It can last, the sample can last up for 9 years. Once again, we could have had this for 30, 40 years. The 1898 or whenever Lawrence was founded, we don't know. So it's really not that much of a shock to see that we got some weird looking stuff in our mass specs. So ideally, I'd really like to purchase a new river sediment A standard to look at if my soil extraction process worked. However, it's $1,105. In the chemistry world, this actually might not seem like a lot if you're trying to make different fluids for viscosity and stuff, but but my conger mix is about $50, which is, I mean, for a senior experience budget, that's pretty good. So we want to avoid that if possible, and eventually we want to see if we can actually extract PCBs from the soil is the end takeaway message. So during this talk, and for all the help throughout the year, I'd like to thank Professor Dever, who I think is back there. Who was there? Okay. He helped a lot with the leak in the fall term. We didn't fix it, but we got a lot closer, and I had a lot of questions about the mass spec reading that he helped a lot with. Daniel Martin and everyone in the chem stock room for constantly bugging them for things like clickers to liquids. And lastly, Dr. Janet Donahue for all of her help throughout these last 4 years. She's been a huge help, whether it's here in senior experience or if it's us traveling to the Bakken Formation. This is our last field site, and then this is her kicking back on one of the hot days and making Julia do all the work. But she's been an absolute great resource and has done so much for me. So thank you so much. Read about any articles, general sources, and do we have any questions? More.
For how long PCBs last in the environment, do the number of chlorines affect how long they'll?
Yeah, so the more chlorines there are, just the longer that it's going to stay around, so it's more inert. Good question now. Chris?
So you're looking at overall concentrations of PCBs, hopefully in river sediments. Why does it particularly matter that you figure out whether it's PCB 18 or PCB 21, as you just want to figure out how many PCBs are overall?
Yeah, so I guess that kind of pairs with Lauren's question. That's a really good point. Ideally, we would just care, there's a bunch here and we just want to get it out. But if we're looking at the half-life, we really want to make sure that if we do have really high PCB concentrations, we get those the heck out of the Fox River, and we just remain some smaller stuff behind, if that helps. So,
When you say half-life, do you mean retention time or you mean how quickly they break down?
how quickly they break down. Is there your hand?
Oh yeah, I was just wondering how you decided on your extraction technique, kind of did you get that from a paper? Did you just try it on your own?
Yeah, that was from the SOP, the first one that I used. That was all the parameters for the RAM cycle time and stuff. It said to dissolve it in dimethylchlorine or dimethylchloride, DMC, and I did that at first. It didn't give a very nice graph, so I tried hexanes. It worked a little bit better, but yeah, you still saw all that weird stuff in it. So I just used an organic solvent. I think was the.
So do you think you're getting a lot, obviously from your commander, you're getting other things too, so do you think there is a technique to specifically pull off PCBs?
I'm sure there is, for the most part, that NIST standard, extracting that's pretty easy because it's just PCBs left over and everything else has been sterilized. But if I wanted to actually go out and dig in the Fox River, yeah, I'd have to use a lot, a different method, yeah, a lot more intense extraction, which I didn't get to look into too much. Chris again.
When you started out the talk, you talked about a little bit about some of the health hazards of PCBs. It didn't seem as if they were, I don't want to be assumptuous, as serious as you'd think they were for as much funding the EPA is putting into there. Is there some additional health hazards that have been discovered in the last 50 years?
Yeah, so I didn't know where to put that really. Yeah, after they're first introduced, we see those little zits. Not a huge deal, but it is listed as a carcinogen now, high amounts that we learned later after we studied a lot. So yeah, we do want to, they do matter, I guess, is the takeaway message.
Let's thank our speaker.